Alright, so on our last online class, we introduced a few ideas in our exploration of motion, the concepts of momentum and impulse. The main concept is that the momentum is the mass of an object times its velocity. The momentum is a vector because velocity is a vector, and we can find the change in momentum caused by force by calculating the impulse. This impulse is the force times the time that the force has been applied. Impulse is also a vector, right? So as force is a vector, force times time must also be a vector. And if we know the impulse, then we know by how much the momentum of an object has changed. One reason that momentum is such a powerful concept in understanding motion is that the momentum of a system with no external forces is conserved. If we know the initial momentum of a system, and that all of the forces acting on a system are acting on each other, then that will equal the final momentum of the system. No matter how complex or messy the forces and the number of particles in the system, this must hold true. The reason for this is that for every force, there's an equal and opposite force, right? If you push on a table, then you feel the table pushing back on you. So this is Newton's third law. This means that if every force has an equal and opposite force, then each impulse must have an equal and opposite impulse. So the net impulse of any system where we are considering both the force and the reaction force, then the net impulse must be zero. If the net impulse is zero, then the change in the momentum must be zero. Notice if we're playing pool here and hit a cue ball into another ball, the impulse on the cue ball is equal and opposite to the impulse on the 8 ball or whatever ball we've hit. Each ball experiences an impulse, but the sum of those two impulses add up to zero because they're pointing in opposite directions. Okay, let's try a visual version of an example problem. So in this case, we have a block number 1 that collides with a stationary block number 2. There are no net forces acting on a system, we're just colliding two blocks. They're putting forces on each other. So we want to draw the momentum vectors with the correct magnitude. The red arrows tell us the momentum of the system that we know, and then we'll fill in blue arrows by using conservation of momentum and deduction. We are told that block 1 has an initial momentum of 4 kg per second, and that block 2 is stationary. So its momentum is 0 kilograms per meters per second at the start. After the collision, we are shown that the momentum of block number 2 is 2 kg per second to the right. Now we want to find the final momentum of block number 1. We know that there are no external forces on the system, so the initial and final momentum must be the same. That means we need to know the initial momentum. Well, since block number 1 starts out with 4 momentum and block number 2 has no momentum, then we add them together and we get the total momentum to be 4 to the right. Next, we want to find the final momentum, and so here this must be equal to the initial momentum. So it turns out then it's just the same as the initial momentum, right, due to conservation of momentum. Now we'd like to know what the momentum of block number 1 is. So we know that the sum of the momentum of block 1 plus block 2 after the collision must add up to 4. We know that block 2 is 2, so the momentum of block number 1 must also be 2. So we can do our sanity check, and so our block number 1 plus block number 2 must equal the total momentum. So 2 plus 2 is 4, so that all checks out. We are also asked for the changed momentum of each block. So block number 2 changes from 0 to 2, so its momentum increases by 2, and the momentum of block number 1 changes from 4 to 2, so its momentum decreases by 2. So its momentum points to the left by 2. I haven't put numbers on this, but if you knew the masses of the two blocks, then you could divide the momentum by the mass in order to get the velocity of the blocks. The key idea here is due to the conservation of momentum. If you know the momentum of an isolated system before a collision, and then you know the momentum after the collision, then no matter how complex the forces acting in the system are, that final momentum and initial momentum must be the same. And then if you have the momentum of one of the objects after the collision, if there's two objects, then you can solve for the momentum of the unknown object. Let's do a similar example, but this time we're going to put some numbers on it. So here we have two figure skaters, and they start at rest, and they push against each other. One has a mass of 54 kilograms and is moving, and after it gets moving, or she gets moving, she has a velocity of 2.5 meters per second after they have separated. So what is the velocity of the second skater who has a mass of 88 kilograms? So we have our two skaters, and they start out at rest, so the initial momentum is 0. That means that the final momentum also must equal to be 0 because of conservation of momentum. Now we know that the final momentum must be 0, then that means that the sum of the final momentum of our one skater plus the final momentum of the other skater must add up to be 0. Next, we know that due to conservation of momentum, that the sum of our m1 plus a velocity of 1 is equal to the mass of 2 times the velocity of 2. Now we can plug in what we know. So we know that in one of our skaters, they have a mass of 54 kilograms and a velocity of 2.5 meters per second, and the other has a mass of 88 kilograms and an unknown initial velocity. So we know that the sum of those two momentums must be equal to 0. So we know, first of all, that the velocity of the second skater must be to the left, because in order for the total momentum to go to 0, if one is going to the right, then the other has to be to the left. And then if we do our algebra here, so 54 kilograms times 2.5 meters per second of our one skater plus 88 kilograms times the velocity of 2 is then equal to the momentum of the second. So we can separate this out and subtract 88 kilograms of V2 from both sides, and then we can divide by the negative 88 kilograms to solve for the velocity of the second skater. So if we do that, we find that the velocity of the second skater is a negative 1.53 meters per second. So notice the velocity is negative because the second skater needs to be moving in the opposite direction as the first skater. Also notice the heavier skater must have a velocity with a smaller magnitude, while the lighter skater must have a velocity with a larger magnitude. Okay, so we've coded up some similar problems for you. This question is about the recoil of a rifle. So essentially the momentum of a bullet that flies out of the rifle will be equal in magnitude as the momentum of the rifle moving backwards. So using conservation of momentum, you can then solve for the unknown velocity. Good luck.